Amos around. Thanks to Amos. And for the opportunity to visit Israel again and the invitation to give these lectures. It's always very nice to be back. Okay. My lectures will be on simplification of the classical equations of gravity that occurs in the limit of a large number of dimensions. Okay? To motivate these lectures, and to set the stage for the introduction to these lectures, let me start by reminding you of the ADS-CFT correspondence. The ADS-CFT correspondence, as all of you know, is the statement that some quantum field theories are identical or can be rewritten as theories of gravity. Okay? So the ADS-CFT correspondence tells you that you have some quantum field theories and they are theories of gravity. Another way of saying the ADS-CFT, another way of saying this is that some gravitational theories are, perhaps all, but at least some gravitational theories can be rewritten as non-gravitational systems. This was a big surprise when we first discovered this 20 years ago. And this surprise seems like an inherently quantum. As you know, the non-gravitational systems that get rewritten as gravitational theories are non-gravitational and very strong values of the coupling. This seems like a very, very quantum statement. Nonetheless, you could ask the following question. You could ask, is there a context in which something like this happens classically? Is there a context in which you can take theories of gravity and just classically rewrite them as non-gravitational systems? The answer to this question is yes. And there are two contexts in which it's well understood that the answer to this question is yes. The first is an old story. It's almost 10 years old now. It's a story that happens inside asymptotically ADS spaces. And it's a story that involves hydrodynamics. It goes by the name of the fluid gravity correspondence. The second is a newer story that developed over the last 3 or 4 years, and is an equivalence between gravitational dynamics of black holes, let's say, in flat space, and other non-gravitational systems. So my lectures will mainly be about the second story, but to set the tone for the lectures and to present many of the ideas in a more, to some of you, more familiar setting, much of the first lecture will be a review of the first story, namely a review of the fluid gravity correspondence, just so that you can see how the story with largely black holes sort of rhymes with the fluid gravity correspondence. Okay, so what we're going to do in much of this first lecture is to work with gravity in asymptotically ADS space. Okay, so we're going to work with the equations of the equations we're going to study are gravity with a negative cosmological constant. Okay, so Einstein gravity with a negative the only fields in the theory are metric. You can complicate the story by adding more degrees of freedom, but in this brief reminder lecture, we're not going to do so. Okay, so when you suitably scale the cosmological constant, there is, of course, a famous solution to these equations, which is in the ADS space. I'm going to write ADS space in Poincare coordinates. Okay, ADS space in Poincare coordinates, and a choice of Poincare coordinates can be written as follows: dr squared by r squared plus this is simply ADS space, radius 1 if you like, in Poincare coordinates. This is formula 1 if you know. There's another famous exact solution to these equations. Okay? And that other solution is the following. For concreteness in these lectures, I'm working in ADS 5. Okay, so I'm working with 5-dimensional gravity with cosmological constant. Everything I say works in arbitrary numbers. But just to be totally concrete, I work. Okay, so the second solution that's perhaps not as well known as the Poincaré solution, is also a very well known solution of these equations. Okay, is what's called the black brain. Okay, this solution has, like this, is 5 coordinates. The coordinate R, the coordinate T, and 3 spatial coordinates. The solution is translationally invariant in the xi and t coordinates. D by dxi and d by dt are Killing vectors. And it takes this form. Notice that this solution reduces to this solution when R is large. Pi t, pi is 3.14, blah, blah, blah. And t is an arbitrary constant. Okay? Just from the point of view of solutions to general relativity, you could replace this by an arbitrary constant, but t is going to have a physical interpretation. Okay, for every value of this constant t, this is a solution. Okay, this solution has an event horizon at r is equal to pi t. This is a familiar thing. It's sort of like the Schwarzschild solution, the place where dt, the coefficient of dt squared goes to 0 is an event horizon. It's very much like a Schwarzschild solution. Okay, the coefficient of dt squared goes to 0, and the coefficient of dr squared goes to infinity at the same point. This is a Schwarzschild type event horizon. This solution is called the black brain. By the end of this lecture, I will give you a physical interpretation of what's going on. But for now, we'll stay away from these interpretations and just do some algebra and build up this interpretation. Okay, so this black brain is another solution of Einstein's equation for the negative cosmological constant. It's translationally invariant, and apparently is a solution that represents some stuff uniformly all over the x and t directions. This stuff is going to turn out to be thermal stuff, as all of you know, but we get to that at the end. Okay, now, suppose you were interested in understanding the dynamics of this black brain solution. Something that you might do is the following. You might like to take Einstein's equations and linearize them around this black brain. Okay? If you did that, okay, so what you might try to do is take Einstein's equations for the negative cosmological constant and linearize them around the black brain. Now, you can then go ahead and solve these linearized equations with subject to some boundary conditions. Okay? Now I'm going to tell you what boundary conditions we're going to be doing this solving. The boundary conditions at large R are the boundary conditions that every component of the metric die off like a power 1 by r to the 4 relative to the non-zero component in the background. So for instance, GII should scale like r squared, which is what it is in the background, times order 1 by r to the 4. These boundary conditions are familiar from the ADS CFT correspondence. If you try to solve linearized Einstein's equations in the ADS background, you find two kinds of solutions. Those that go like r squared times constant, and those that go like r squared times 1 by r to the 4. And the usual rules of the ADS CFT correspondence tell us that if we take the field theory of the boundary and don't perturb it with the source, then we're not allowed to have constant type that fall off at infinity. However, we are allowed to have this 1 by r to the 4 fall off at infinity. The coefficient of this 1 by r to the 4, loosely speaking, is identified with the stress tensor of the field theory in the particular state that you happen to be looking you happen to be studying. Okay? So if we take some state, you smashed that state, its stress tensor oscillates around, you're allowed to have this. Okay, so this boundary condition from the point of view of the ADS CFT correspondence is simply the boundary condition that tells you that you're looking at the original field theory, not the field theory perturbed by some other operator, not the forced field theory. There's a second boundary condition which we'll state more precisely as the lectures go on. Also, we'll state this precisely in the context of real interest in these lectures, namely largely black hole correspondence. Remember, this is just a reminder of stuff that is similar to what we actually been interested in. Okay, the second boundary condition, but it's sufficient for this linearized level state. At this linearized level, a sufficient statement for these boundary conditions is to say that all modes are taken to be ingoing at r is equal to pi t. The ingoing at the event rate. Okay. Another way to say this is that if you move to ingoing Eddington-Finkelstein coordinates, all modes will be regular. The modes that we look at will be regular in these coordinates. The other possible kind of modes that are outgoing, the modes that try to sit along the horizon, become irregular in these Eddington-Finkelstein type coordinates. So it will start looking irregular. Okay? So we put these two boundary conditions on the problem. We put these two boundary conditions, the boundary condition normalizability at infinity, and ingoingness at the event horizon. And now what we've got is a particle in a box type mode. Okay? We've got an equation that's something like a wave equation. It's a linearized Einstein's equations with two boundary conditions. One boundary condition at infinity, another boundary condition at pi t. And you can try to solve this particle in a box problem. Now, as many of you know, even though the ADS boundary is at infinity, it dynamically behaves as if it's at a finite distance. For many purposes. Okay, certainly for the purposes that I'm telling you about now. Okay, so even though this box that we're looking at has an infinite proper size, for dynamical purposes, it's a box with a finite effective size. Okay? So now, when you've got a box of finite size with two boundary conditions at the ends of the box, you've got a wave equation, you solve for the spectrum of the wave equation, you get a bunch, and so what you're trying to do is to solve for omega as a function of, let's say, k. Okay, where k is some sort of measure of the radial independence of the solution. Okay? When you've got a problem like this, you find a discrete set of modes. Omega is equal to omega, which depends on n, which is roughly the number of harmonics between the two ends of the box. Now, in all of this, I suppress something important. We've got translational invariance in the xi directions. So all our modes are taken to scale like e to the pi ki xi. And then I convert this problem to this one-dimensional box problem, where I convert this for every value of k. So this omega here is a function of n and k. Okay? N is some schematic for the number of nodes between the first end and second end of the box. K is the momentum within the mode. Okay. So you can try to go ahead and solve this problem. And when you go ahead and solve this problem, you get some very complicated answer. Now, to try to make sense of this answer, a limit you can look at, it's always often a useful limit to look at in a physical situation, is look at the long wavelength limit. Namely, the limit k goes to 0. So if the limit k goes to 0, you can try to study the frequencies of all modes of the world. Now, so suppose we take a strict limit k goes to 0, for almost all of these modes, the answer turns out to be, the limit k goes to 0, turns out to be some function of n times t. Okay? This function of n is some complicated function that we're not interested in. The important point here is this t. Where did the t come from? It just came from dimensional analysis, or scale invariance in ADS space. By scale transformation, you can get t out of the bottom. But that same scale transformation will scale omega by a factor of, sorry, I even said it wrong. Yeah, no, I said it right. Yeah. It will scale omega by a factor of t. So the t dependence true for all modes, except some modes can be special. Those modes are special that have f of n is equal to 0. It could be that you have some modes with f of n equals 0. Then you get a scaling like 0 times t, but that's just 0. Okay. So if you've got a scaling like 0 times t, you've got to be more careful. You don't want to take the strict limit that goes to 0, you want to see how it goes to 0. It turns out that if we're in 5 dimensions, there are exactly 4 modes that scale for which these f of n go to 0. Okay? For 2 of these modes, omega goes like k, in fact, k by square root 3. Plus minus k by square root 3 plus I. And for the remaining 2 modes, omega goes like k squared, and I times k squared by t times some number, if you remember, plus I. Okay? So there's an infinite number of modes, the modes with infinite number of wheels between the two ends, for which omega and in the long k, in the short k limit, is t, and then there are a finite number of modes, just 4, for which omega goes to 0 in this particular way. Now this is interesting. Why is it interesting? It's interesting because it's a basically general rule in physics that anytime you have a physical problem which displays a scale separation, you have a few modes that are much lighter than all the rest of the modes which are very heavy compared to lightness. Then there's simplification in physics where we look at the effective theory of just the light. And this is a situation in which we see that. Because we've got a few modes, namely 4, which are very light when k is very small, compared to all the other modes whose mass, which is omega, is over t. So you could ask, in this situation, is there an effective classical theory of gravity? An effective classical theory of gravity that keeps only the light degrees of freedom. These 4 modes. At the linearized level, just by solving the equations, we found this theory. But that's not the interesting question. The interesting question is, what is the non-linear effective theory of the light? This question? Where do I see 4 modes? I'm sorry, I didn't say it properly. Omega is plus minus k, that's 2, that's plus and minus. And here, omega is k squared by t. There are 2 such modes, one for each I. I did say it properly. Let me say it properly. You know, you've got these modes, and they've got a particular direction in which k is going. Now you've got 2 spatial directions orthogonal, and these 2 modes transform like a vector under rotations of these two spatial. So those are 2 modes with a certain vector index that are not written. Thank you for the question. Other questions? Yes?
Where does this plus minus come from, since we are in the window in
Yeah, now you know, one should be careful. This k is k along the xi directions.
Yeah, which is the different direction.
Which is one of the field theory directions. There's also k along the radial direction. Now, this ingoing tells you what to do with k along the radial direction. But it doesn't tell you what to do with k along the xi direction. Okay? So this is unrelated to that. Okay? It's a good question. Other questions about it? Excellent. So, we've got these 4 modes, and we want to try to make a non-linear theory of these 4 modes to try to effectively simplify gravity. In the long wavelength limit, keeping the degrees of freedom that make up these 4 modes, but at non-linear. What I'm going to show you is that this attempt gives you a non-gravitational problem. It turns out to be a famous non-gravitational problem, but we'll see that. Okay? So now, our problem is to try to understand the dynamics of these 4 modes. How are we going to go about it? We want to do this non-linear. The first thing is to try to understand, why are there 4 lines? Okay, you know, again in physics, there's a limited number of ways in which massless modes are produced. You can take them off in your hands, gauge invariance, blah, blah, blah. Well, one way, you know, one generic mechanism that gives rise to the right modes is spontaneous symmetry. Okay? If you've got a situation where your vacuum, the place about which you're expanding, has a parameter, and that parameter preserves translational invariance. So you've got a 0 mode that preserves translational invariance. The basic idea of the Goldstone phenomenon should give you light modes. So the next question we're going to ask is this a context, is this what's happening in this situation? We've got this black brain. How do we have light modes because of the Goldstone phenomenon? And the answer is yes, as I'm going to try to convince you. See, firstly, this solution here breaks 4 symmetries of relevance. The first symmetry breaks the scale limits. You set any given value of t. That breaks scale limits. But if you take the solution with 1t and scale it up, all it does is give you a solution with another t. Okay? Therefore, t is one of the parameters in your solution that preserves translation. But there are other parameters in the solution that preserve translation. You don't see that because I've not even done the most general solution. How do you see this? You see, what we've got here is a special coordinate t. There's something unnatural about this solution if you think about it. Because I've singled out one of the field theory directions, the special. It's the direction behind which we have the 1 minus pi t 4 by r. Well, the others are different. Okay? So this solution can be written, well, this solution can be written in a way that doesn't make one coordinate special. But actually, in order to do that, not have to do it twice, I'm going to first rewrite the solution, the Schwarzschild type solution, in another coordinate system, which will prove very useful for my analysis. And then do the generalization in that coordinate system. Okay, so why I'm changing coordinates will become clear in 5 minutes, but for now it's just a quirk. Okay? So what I'm going to do is to change coordinates to what I call Eddington-Finkelstein coordinates. So what are Eddington-Finkelstein coordinates? Eddington-Finkelstein coordinates are coordinates in which, first, just for this solution itself, r is r. Okay, coordinate r is not changing. But we define a new coordinate, we define a new coordinate v, which is t plus integral dr divided by f of r. Where f of r is whatever appears behind dt squared. Oops, I even know it's wrong. Factor of r squared. Okay, f of r is equal to dr divided by r squared into 1 minus pi t by r the whole to the 4. Now, what is the point of this coordinate change? There are many ways to say this. The one purely algebraic way of motivating this coordinate change is to notice that this coordinate system becomes funny at r is equal to pi t because the coefficient of dr squared goes up at r equal to pi. It means, for instance, the determinant of the metric. Well, it means that the inverse of the metric determines pi. The inverse of the metric is not there. Okay? Now, if you want to change to a nice coordinate system, you want to get rid of this bad feature. One way of doing it is just to make a change to a coordinate system where the coefficient of dr squared just goes to 0. Then in particular it will not blow up. Okay? And this coordinate change is engineered to ensure that. Let's see that. If you put this, you see, this is the same thing as t is equal to v minus dr by f of r. And if you plug this coordinate change into this equation, you see there are 2 places you get a dr squared. That's here. And there's the dr term from dt. That comes with the dr squared divided by f of r the whole thing squared from there. But there's an f of r here. So that's a dr squared by f of r, which cancels this dr squared here. Okay? Is that clear?
F of r already includes integral and
I'm sorry. dr squared by f prime by f prime. Sorry. Yeah. You're absolutely right. Let me not go. Sorry, thank you. F of r is equal to r squared. Now what I said was right. Okay? We get a dr squared by f of r here, because that's the definition of f of r. Okay? Here we get a dr squared by f of r, the whole thing squared from here. But it's multiplied by f of r. So it's a dr squared by f of r, opposite signs that cancel. The same mechanism that makes the dr squared term cancel makes the dt dr coefficient very simple. Because there's 1 by f of r from the coordinate change, but there's an f of r outside. And so when you make this change of coordinates, you see that the metric is ds squared is equal to 2 dv dr minus dv squared f of r plus r squared dx. It's 2 minutes of that. Check. This is sort of nice because now we don't have this unpleasant 1 over f of r. Okay, now in this coordinate system, I could have done the original one, but it's convenient to do this one for what I'm going to do later on. I can now generalize this solution to the following. ds, I can write ds squared is equal to minus 2 u mu dx mu dr minus p mu nu dx mu dx mu f of r plus r squared plus u mu minus u mu dx mu f of r, where for this solution u mu is equal to minus 1, 0, 0, 0. So far all I've done is take a simple solution and write it in a way that looks complicated. Hey, you just plug this in, here you get back. The point of writing the solution is this clear. The point of writing the solution in this way is that there is an obvious generalization. And that generalization is obtained by taking the solution and boosting it. You see, that solution represents stuff at rest. It singles out dt. Now, you can take the solution and boost it, by which I mean just make the coordinate change, the Lorentz coordinate change in the x mu coordinates. That's not an invariance of the solution because it singles out dt. But is an invariance of the solution written like this if you accompany the boost by a boost of u. Okay? So all that you get by boosting the solution is getting this solution with a boosted u. But by boosts, starting from 1, 0, 0, 0, 0, minus 1, 0, 0, 0, you can produce any 4 velocity that squares to minus 1. So now we've got a bunch of solutions labeled by temperature and u mu, where u mu is an arbitrary 4 velocity that squares to minus 1. Okay? We've done nothing. Somebody's done the hard work, solved Einstein's equations here, and then we notice that we can generalize that to a 4-parameter set of solutions. So far, this is playing with limits. Okay? However, the important thing about this playing with words is now we identify the Black-Brane solution as one solution in a 4-dimensional manifold solution. Note the 4. It's the same as the number of line points. Okay? It's one solution in a 4-dimensional manifold solution. So now you could ask, maybe what's going on is the light modes are just long wavelength fluctuations of these parameters by the Goldstone logic. Okay? So you could ask, maybe what's going on, you could suggest, and maybe what's going on is that we'll find new solutions to the equations of motion by studying this object when we take u mu not to be a constant, but to be u mu as a function of x. Now x mu is always. And similarly, t not to be a constant, but t is equal to t of x. Yes?
What is the P mini that you have there?
I could hear. Say
The
it.
P mini that you have there?
Thank you. I'm so sorry. I should have written that. I'm sorry. P mu is the projector of combinator to the fourth. Okay. I'm sorry for this. Please keep doing this. Okay? Great. Thank you for the question. Okay. So you could ask, what happens if I take this metric and function of x mu, t is a function of x. And the answer to this question, you might think then that, when u and t are constants, we get solutions to Einstein's equations. You might think that if u and t vary slowly enough, you'll get almost solutions to Einstein's equations. Okay? So let's test out this. If you try to, I'm going to go through this very fast because this is just a reminder. It's just an introduction. But, okay, if you try to test out this idea, you can try to solve Einstein's equations. Just take these configurations and plug them into Einstein's equations. Now, Einstein's equations break up. When you've got a distinguished coordinate, it's often useful to take Einstein's equations, which are whatever they are, right? R mu minus G mu R by 2 plus some number which I don't remember, that's lambda G mu lambda some number that I don't remember is equal to 0. So let's call this whole equation A. Now you can take this equation A mu and dot it with the one form dr. See, R is a coordinate that's playing some special role here. It's clearly different from all the other directions. You take these equations and dot it with the one form dr. And so there are these equations, from the point of view of R evolution, are called constraint equations. The remaining equations, the equations that are not, where the free indices are not those dotted with the other coordinates, the remaining equations are called the dynamic equations. And within Einstein's equations, okay, the constraint equations and dynamical equations play logically distinct roles. If you're interested in the equations evolving in the R direction, if you're interested in the equations taking data and evolving the data in the R direction. Okay, the role of the constraint equations, the role of the dynamical equations is the traditional role of equation motion. It takes data on a slice and evolves it forward. The role of the dynamic equations is different. It's connected to the fact that gravity is against it. What it does is give you a constraint on data on your slice that can be correctly evolved forward. Okay? The dynamic equations tell you how things evolve in R. The constraint equations tell you what allow the data evolve. You're allowed to put it in slices so that you can evolve. Now, a great feature of Einstein's equations, the consistency, is the feature that if you solve the dynamic equations in one slice, and then you take the data and evolve it by, you decide the constraint equations in one slice, you take this data and evolve it using the dynamic equation, the constraint equations will automatically be solved in every slice. If that wasn't the case, we would have it inconsistent. But it is the case. You can prove it. Okay? So, in order to solve Einstein's equations, you need to solve the dynamic equations everywhere, and the constraint equations are only one slice. One slice in R. Now,
The boundary condition.
what?
Boundary condition?
The boundary condition is a boundary condition in the solving of the dynamic equations, and we need to talk about that. But for the statement that I made, there are no boundary conditions. The statement that I made is true without any boundary conditions.
It's more like the initial condition.
The initial conditions, right. What you would have to do is to take some data on one slice, that's like your initial condition, and evolve it to later R. Okay? But once you've done that, you still need to solve the constraint equations. And if you solve these constraint equations on any one slice, on one quote-unquote initial time slice, you'll automatically solve the constraint equations anyway. This is not clear?
So you have to do, after imposing initial condition, you have to further solve.
Yeah, let's say this again. If we were, R is not really time, but let's forget about that. Suppose R was time. Okay? Then the slice here would be an initial value slice. So, you put data on the slice, the equations of motion should tell you, once you know what the data on the slice, should tell you what the data is at all data, quote unquote, times. That's takes data on the slice, the initial value of data on the slice, and evolves it to future. However, Einstein equation is more than, let's say, del square phi. Okay? Del square phi is equal to 0 would do just this. Take data on one slice and go. However, Einstein equation also has the constraint equation. The constraint equations tell you can't put arbitrary data on the initial slice. The data that you put is constrained. Okay? Only that constrained data can be evolved. But once you put the correct data that obeys these constraints, you don't have to check at any future time whether the constraints are still obeyed. It's automatic by the structure of Einstein's equations that if you obey the constraint equations on one slice, you'll obey them for all future slices. This is just general property of Einstein's equation. Please.
So you mean the constraint equation, the solution of the constraint equation is automatically the solution of the dynamic?
No. Given the initial data, a constraint equation constrains data on the space.
Yes, but if you say we don't have to check again and in future.
Yeah. If the constraint equations are obeyed on one slice and the dynamical equations are obeyed everywhere, then the constraint equations are obeyed everywhere. The dynamical equations are such that they take data that obeys the constraints and evolves it to data that also obeys the constraints. Is this clear? Yes?
So regarding this example, the constant equation is going to put constants on u and t, and then dynamical equation will give you the R evolution.
Exactly. That's exactly right. We're going to see that. Okay. So these. Okay. So we'll imagine now that we've plugged this stuff in, and we take this answer and we try to plug it into Einstein's equation. We have to solve both the dynamical and the constraint. Really, logically, we should solve the dynamic equations first. Doesn't make a difference which order you solve the equations. So let me first try to solve the constraint equations. Since I've not yet solved the dynamical equations, it matters where I put these constraint equations. I'll choose a particularly convenient slice. The slice R equals infinity. At that point, you can ask, what are these constraint equations? If this was the first time we'd see gravity in an asymptotically de Sitter space, we would have to think about it. But it's not the first time we've seen gravity in ADS space. All of you know all about ADS CFT. And one of the things that you know is that the constraint equations at large R are simply the equations d mu, t mu nu is equal to 0. Where t mu nu is the boundary stress tensor, the stress tensor of the dual boundary theory associated with the solution, the solution we studied. And there is a well-known prescription for how to compute this t mu nu given any particular metric. The thing about this equation that's important to me is that this equation comes with a derivative. So you see, our program tries to solve this equation in an expansion in derivatives, expansion in boundary derivatives. That's why we start with a solution which was constant in space. And then slowly varied, we'll solve the equations order by order in a derivative expansion. This equation already comes with one derivative. So if I want to keep terms only to one order 1 in the derivative expansion, I need to keep only the terms that are leading order, 0 order in the derivative expansion, in t mu nu. But if something 0 order in the derivative expansion, then you cannot distinguish the formula for t mu nu in this varying solution from the formula for t mu nu in the constant solution. Because only derivatives distinguish between things that vary and the constants. And so we can just plug in the value for t mu nu in the black brain solution. Okay. Turns out that t mu nu up to some number is, the number is vital, t to the 4. Eta mu nu plus 4 u. So we just take the constant solutions and we use the formulas of ADS CFT, whatever. Compute extrinsic curvatures and compute the stress tensor. For the constant solution, of course you get something that's independent. In the constant solution, it's independent of x. You get this formula. And then, for this equation, you take this formula and plug the solution in, the formula in here, just replacing t with the x-dependent value of t and u with the x-dependent value of u. So the constraint equation, the nature of the constraint equation is very simple. We have it there in front of us. Now, two, three quick comments. Firstly, what did we say about this form of the stress test? How do we know that this is the right form of the stress test? Actually, this form can be argued from symmetries. The factor of t to the 4 comes from scaling. It's the fact that the stress tensor is dimension 4. Okay, just by scaling you can set t to 1, that same scaling gives you power of 1. The fact that there's eta mu nu and u mu u nu, some number times this plus some number times this, well, what else could it be? You have to sort up the indices. And the fact that the relative coefficient is 4 is the fact that the stress tensor is fixed. Trace of eta is 4, trace of u mu is -1. Okay? So, up to some number which you have to do some work to compute, and anyway, the conventions will all that. But the form of the stress tensor didn't need to do any work. Okay, great. Now that you have this, you see that what you get is a solution to Einstein's, that if you want Einstein's equations to be solved, you need to solve this equation. And now things become interesting. Because you see that what we've got is a new effective dynamical system. Why do I have a new effective dynamical system? It's because, to start with, in our simple-minded generalization of this black-brain solution, we took temperature and u mu to be arbitrary functions of x mu. However, we've seen that if we want to take this simple-minded ansatz and promote it to what will be the genuine solution of Einstein's equations, these x mu, these u mu and t cannot be arbitrary functions of x mu. They have to be those functions that satisfy a particular equation of motion. And this equation of motion is simply this equation, where e mu nu is given by this formula. Why do I say that this isn't another dynamical system? It's by counting. How many variables did we have in u mu? The number of variables we have in u mu are 3. There are 4, because 4 indices, but u squared is -1. And we have 1 variable in t, so we have 4 variables. How many equations do we have here? Well, we've got 4 equations. Because there's 1 free index, and each free index gives you an independent equation. So we've got 4 equations for 4 variables. So plausibly, a well-defined dynamical system for these low-energy degrees of freedom, u, mu, and t. Okay? You see, so this sort of uncontrolled idea of make these u's and t's to be any functions of x mu becomes suddenly very interesting. These functions are not free, they obey dynamics, a new equation. Okay, now just to complete very quickly, before we get to the real problem of interest in these lectures, just to complete the structure of this game. So far we solved the constraint. However, now we also have to solve the dynamic. The interesting thing about that problem is A, that it's solvable, order by order and derivative expansion, and B, that the solution with appropriate definitions, which I will not get into here, is unique. That is, with appropriate definitions, given u mu and t as functions of x, the correction of this ansatz to first order in the derivative expansion is uniquely determined by the equations. I won't go through this for you, okay? Because that will take too long. Okay? Take my word on it. Please ask me if the meaning of what I'm saying is not clear. Given u mu and t, you can take these equations, you get some differential equations in R, you can solve these differential equations, and you find an answer that once you impose all physically relevant boundary conditions and impose all a particular physically relevant definition of what it means, what u means at higher order than derivative expansion, t means in higher order. Something Amos knows very well, yeah? Okay. Once you impose all those definitions and physically relevant boundary conditions, you get unique solution. Okay. A feature of the solution is that in addition to these terms, you get various other terms at first order. One term turns out to be sigma mu nu times some function of r, where sigma mu nu is equal to half del mu u nu projected. So let's call it sigma alpha beta p mu alpha. Okay, minus okay, it's the symmetrized derivatives of velocities with trace relief. Okay? So, to first order, we've solved this program of finding a new set of solutions of Einstein's equations based on an old set. The old set being just these black lines. Now, you can just replay the tape. Starting with this solution, you can now try to find the solutions to second order in derivative expansion. The first thing you will do is to impose this equation. But now T mu nu is not this. Because T mu nu is now the stress tensor dual to your new solution. And in particular, it has contribution coming from this additional term in the metric. That contribution turns out to go like some number times T cubed times sigma mu. Okay? Turns out this is the only additional contribution to stress tensor. Okay? Then you solve the constraint equations and move to the next order. And then you can play the game again. At next order you get another correction to Einstein to the stress tensor. Next order you get another correction and so on. So you get an infinite number of corrections successively suppressed by, in the derivative expansion, corrections to the stress tensor. But the important point is that whatever you get is just a function of temperatures and velocities. It's a determined function of temperatures and velocities. So the basic counting, the number of variables was 4, the number of equations, never changes. So you get successively more complicated equations at higher and higher order in the derivative expansion. But always, at least from parameter counting, from counting of number of variables and functions, the numbers work out. So you've always got a closed dynamical system. Okay? So we've discovered this marvelous thing. The thing that we've discovered is that in a particular context and in a particular long wavelength expansion, if we're interested in solving Einstein's equations in asymptotically anti-de Sitter spaces, we found the duality of this question to another question. And the other question is finding solutions to this strange set of equations of motion. The variables of this strange set of equations of motion are temperatures and velocities. And the equations are the equations of Rindal, conservation of the stress tensor, with particular constitutive relations, expressions for the stress tensor as functional terms. Great. Now in the last, can I have 3 more minutes? Yes. I will gone slower than I expected, I hope, but let's finish this introductory part, please. In the last 3-4 minutes, let's remind ourselves that actually what we found is not some it's not some that we've hit upon a system that nobody's seen before. The system, if you think about it, is what you should have expected. What we found, the equations that we found have a name. They call the equations of hydrodynamics. And it's a famous expectation in the study of quantum field theories or study of physical systems that under appropriate conditions, at long wavelengths and at finite temperature, all systems are governed by the equations of hydrodynamics. In this context, relativistic generalization of the Navier solution. This is an expectation that is 100 years older than the invention of gravity. Okay? So, if you take the ADS-CFT correspondence, the statement that asymptotically ADS gravity is due to a field current, then you should have expected that there is a context in which the equations of gravity simply become the equations of hydrodynamics. Because if that were not the case, then either that old expectation is wrong in this context, or ADS-CFT is wrong. Okay? Hey, when that should have all have. Okay, we stop. Okay. So, in fact, this expansion is how a modern field theorist would think of hydrodynamics. You see, hydrodynamics is the theory of locally equilibrated stuff. Locally equilibrated stuff is characterized by a local temperature and velocity, And hydrodynamics is the theory of the evolution of the parameters in local equilibrium. In my colloquium today, if few people are motivated to attend, we'll go through some of this in more detail. Okay. Okay. So, what have we done? What have we done here? In today's lecture, what we've done is to discuss a situation in which we took a solution of gravity that had some parameters, a context in which we promoted these parameters to fields, and then by simple following your nose, realized that you could produce an effective dynamical system for these fields. This effective dynamical system contains all the information of gravity in a derivative expansion for the class of solutions we're looking at. Okay? And so we've discovered an interesting classical equivalence between two different dynamical systems. The first is the equation of gravity, and the second is this other strange system, except it's not so strange, it's older than gravity. It's the equation of hydrogen. Okay? This, as I mentioned at the beginning of my lectures, is a by now well-studied phenomenon. It's called fluid gravity correspondence. It's not just studied, it's had many applications. It's had many applications, several of which Amos was responsible for, and has had rich ramifications. What I want to say by all of this is that it's not indisciplinary, it's correct. It's correct and it's interesting and it's led to many things. In the remaining lectures, what we're going to study is a newer version of these sort of ideas. We will study the dynamics of gravity, not in asymptotically ADS space, which of course is a very natural thing for a string theorist to do. Asymptotically ADS space is a very natural place for a string theorist to look at after the ADS CFT correspondence. However, if you were interested, if you asked a GR person, what is the simplest theory of gravity, he would say Einstein equations in flat space. That's where we will look. We will study the equations of horizons, the equations that govern the dynamics of horizons in flat space. And we will find something similar. We will find, just to give you a sneak preview of what we find, we will find that the equations of gravity can be rewritten as another non-gravitational system. And this other non-gravitational system is the hydrodynamics of a sort of soap bubble. A bubble whose shape also moves. One of the degrees of freedom will be the shape of this soap bubble. So there will be a soap bubble on which there is a velocity field and everything's wiggling around simultaneously. Okay? Now, what I've explained to you, we needed a parameter to get everything working. That's usually how physics works. You get equivalence between systems if you've got a new parameter. Okay? We needed a parameter to get everything working. That parameter was long wavelength. In what I'm going to tell you about in the next 3 lectures, everything will work only in a strange limit, a limit in which gravity is studied, not in 4 dimensions, 5 dimensions, but in a large number of dimensions, in a power series expansion in 1 over d. 1 over d will be the parameter that will give us control and make everything I'm saying true. Okay, so that's what we study, and we keep that for the remaining 3 lectures. That's it for now.
Questions? You use the derivative expansion.
Yes.
Do we know that in principle there will be no obstructions at higher order for solving the equations if you substitute again and again?
Yes. You can show that there is an algorithmic procedure for solving. So, the equations that arise in perturbation theory have the following structure. There is a differential equation which has a differential part, which is the same at every order in perturbation, and a source term which is different at different orders. But now these differential equations are such that you can solve them once and for all for arbitrary source term. Okay? So yes. However, this is a slightly loose answer because there is in principle a possibility that the source is such that you are not able to impose your boundary conditions. I'm not sure anyone has actually gone ahead and proved that this never happens. But on physical grounds, it's sort of clear that it never happens. I think I could prove it if somebody put a gun to my head and said, you're dead in the day you have proved this, I think. I don't think so. Okay.
Any more questions?
Without the notion of ADS CFT, do you have any other ideas why U and P should be functions of the field theory coordinates?
Well, the ideas, as I said, were basically the most of it. Yeah, well, then you raise a good point. What's very important in all of this is that because we're an anti-de Sitter space, physics is approximately local in field theory directions. If you have both these factors, A, that we've got a solution which depends on a parallel term that is constant along your field theory term, and B, that there's some effect of locality, then the Goldstone idea makes it inevitable that you get light modes by fluctuating it. Okay? But the locality is very important. And of course we've learned now a lot that this locality is correct because of the ADS wall. Right? It's because something here hits the ADS wall, comes back, only a finite distance. Okay, so that locality more or less forces this. So at the level of algebra, this is what you would expect. What's interesting is that what we discovered is not something new, but something very old. And in the remaining 3 lectures, we'll discover something more new. I don't know how new. More new. That's why I wanted to present this introductory lecture, where you use the same ideas and hit upon something that was older than gravity. Now we're going to do this and hit upon something that's probably newer than gravity. Okay.
Let's thank Shiraz again.